Hello and welcome to this video that covers the AQA Triple Science Physics, and this is Energy Test 1, the beginner test. Okay, so question 1, the image shows a student before and after a bungee jump. The bungee jump has an unstretched length of 20 meters, and we can see a before image of a student standing on a bridge waiting to jump down from the bridge, attached to a bungee cord which is attached to the bridge. We've got the river below, and in the second image we have the student who is at its lowest point, and we have an extended bungee cord. So for safety reasons it's important the bungee cord used is appropriate for the student's weight. Give 2 reasons why. Well, the first thing is to consider if the weight is too much. So if the weight is too much, then what will happen is that the bungee cord will snap and the student will fall into the river. So the first thing is that it's important because the bungee cord might snap as the first one. The second one is that the bungee cord might extend. And that means that the bungee cord will extend. If it continues to extend further, so the bungee cord might extend so much that the student ends up down here into the river. So therefore, the bungee cord extend too much. So they're the 2 reasons here why essentially a bungee cord must be appropriate for the student's weight. First of all, it might snap. Second of all, it might extend too much and the student ends up in the river anyway. The student jumps off the bridge and we are given a list of energies: elastic potential, gravitational potential, kinetic, sound and thermal, and we are going to complete the following sentences. So before the student jumps from the bridge, he has a store of. So the student, if we redraw what's happening here, the student is here and is attached to the bungee cord and he has a river below. So anytime you have an object at a really high point, then this will have gravitational potential stored up, ready to use, because it's been pulled. He is at a point that's higher than the ground level, so that when he jumps off, he will experience a potential energy that will convert as he falls down. So initially he has gravitational potential energy. When he is falling, the student's store of energy increases. Well, as he's falling, the energy that is associated with moving is kinetic, so therefore the student's store of kinetic energy increases. So in this situation, GPE is going to kinetic energy. The potential energy is then being transferred to the kinetic energy as the student gets faster and faster as they fall. When the bungee cord is stretched, the cord stores energy as elastic potential. Any object that stretches, for example rubber bands, catapults, etc., they have elastic potential energy as they stretch. So therefore the elastic potential will increase as the bungee cord is stretched. At the lowest point in the jump, when the student is stationary, the extension of the bungee cord is 35 meters. The bungee cord behaves like a spring with a spring constant of 40 newtons per meter. Calculate the energy stored in the spring. So this one you are going to be given, use one of the equations in your equation sheet, which is E equals half kx squared. K is your spring constant, x is your extension, and half is just half. So if we look at the question that gives us the extension is 35, so x is equal to 35 meters and k is equal to 40 newtons per meter. Again, just double check that your units all match up, which they're both in meters, so that's all good. So energy is equal to a half times 35 squared, because that's the extension, times 40. Plugging that into your calculator, you should have a value of 24,500 joules. And that gives you your answer for part C. Question 2, the diagram shows a cyclist riding along a flat road. So here we have some sentences that's describing as the cyclist accelerates, the something energy stored in the cyclist's body decreases and the something energy of the cyclist increases. So whenever we have a person doing something, we call that chemical energy. So humans, when they, human chemical energy. So for example, when they are cycling, running, swimming, etc. So doing some form of movement or lifting something, etc. We say that the human has chemical energy because it's chemical processes in the body that allows you to use the energy, your energy, to do a task. So therefore, as the cyclist accelerates, the chemical energy stored in the cyclist's body decreases. Okay, so we use our own chemical energy. For example, we burn calories, etc. When we're running, the body is using energy so that we can do the movement. And the something of the energy of the cyclist increases. So the cyclist is moving. We treat the cyclist as a whole, the bike and the person together. So therefore, the kinetic energy of the cyclist increases. They are moving faster. As they should be moving faster, the more that they use the chemical energy in the body, because it means they're pedaling harder and harder and harder. Part B, the mass of a cyclist is 80 kilograms, the speed of the cyclist is 12 meters per second. Calculate the kinetic energy of the cyclist using the equation. So this one is a nice question because it tells us exactly what we need to do. So it tells us kinetic energy is a half times the mass, which is 80, times the speed, which is 12 squared. This is very nice because it tells us exactly what we need to do. So your answer is 5,760 joules. For part C, when the cyclist uses the brakes, the bicycle slows down. This causes the temperature of the brakes to increase by 50 degrees. The mass of the brake pads is 0.04 kilograms, and the specific heat capacity of the material is 400 joules per kilogram per degree. Calculate the change in the thermal energy. Again, this is very straightforward. It's given us the equation, which is change in thermal energy is mass times specific heat capacity times temperature change. So therefore, for this equation, the energy or the thermal energy is equal to the mass, which is 0.04, the specific heat capacity, which is 480. So that's there, that tells us there, and the temperature change says it increases by 50 degrees. So we times that by 50. Plugging that into your calculator, you get a value of 960 joules. How is the internal energy of the particles in the brake pads affected by the increase in temperature? So the internal energy of the particles, so if you've got the brake pad here and you've got the particles there, mostly will be a solid, so they will be roughly, it's not a perfect solid, but even though the solid can't move necessarily like a gas does, whenever you add heat energy to a system, the particles will vibrate. So these particles vibrate more. So they stay the same, but the particles themselves will vibrate more, and therefore that shows us that the energy of the system is increasing. And so an increase in temperature will increase the internal energy of the system, regardless of the state. So even if it's a liquid or a solid or a gas, it will always increase. Question 3. A heater uses energy from a laptop computer to keep a drink hot. The image shows a metal mug on the heater. The laptop computer is operated on battery power. How would connecting the heater affect the amount of time the laptop computer would operate before needing it to be recharged? So the laptop is operated by battery. So if we add a heater to this, what would happen is that the laptop has to use its energy to power this heater as well. So therefore, when you're powering something, it decreases the amount of time you need to do it before it needs to be recharged, because it's using the energy faster. So in the original case, if you just have the laptop, if you just do it by itself, it only has the laptop it has to power. But when you have the laptop and the heater connected, so hang on. So if we connect the heater down to the laptop, now we've got two things that we need to power, and therefore we're going to use up more energy. We're going to use up the energy quicker for the laptop, and therefore it will decrease the amount of time so that it needs it before it needs to be recharged. So just be careful of the question and make sure you read the question for this one. For part B, the power output from the heater is 12 watts. Calculate the energy transferred to the metal mug in 60 seconds. So here, the equation for power is power equals energy over time, or work done over time, but we can, energy transferred is the same, E is equal to work done. So it depends, however you remember the formula, they both are the same in this situation. We want to rearrange this formula to get energy. So P equals E over T. You're going to times both sides by T and move it to move it to the other side. So our result is PT equals E. From here we can just plug in the numbers. P is equal to 12 and T watts, and T is equal to 60 seconds. So therefore we can just plug in our numbers. It's going to be 12 times 60, which is equal to 720 joules. Okay, let's have a look at our next question. So our next question is the table. This changes that may affect the energy transfer per second from the heater to the liquid. So in this case, so if we use a mug with a smaller base, then the energy transfer per liquid will decrease. So what does this mean? So if you have a heat, let's say we've got a heater here, okay, and then we have a mug. Okay, so we've got a mug of tea on our heater. Let's say we make a smaller base. So if we make so that's our main one. Let's say we keep the same heater, but now we have a smaller base on our mug. What does that do? Well, it will decrease the amount of energy per second because you've got less of the mug touching the heater. So if you've got less of the mug touching the heater, therefore the energy transfer can't transfer as much, because here it can transfer all of this space here, while on this one it can only transfer a little bit. So therefore we can say that the energy transfer per second decreases. The second one we've got is use a low power heater. Well, P is equal to energy over time. Energy transfer per second is the same as the left hand side, so we can see that here if the power reduces, that means energy over time would have to reduce as well. And then finally, use a plastic mug instead of a metal mug. Well, a metal mug is a good conductor of heat. Okay, so metal is really good, it will transfer the heat very well. If you've ever used a metal pan, most pans, a lot of pans, if you wanted to boil up water, for example, then you could use a metal pan, and that gets hot very quickly because it can transfer the energy very well. Meanwhile, a plastic pan is a poor conductor of heat. It does not transfer heat very well. So therefore, if we want to do the energy transfer per second to the liquid, a plastic mug is not very good, but a metal mug is a great conductor of heat and will transfer it very quickly. And that brings to the end part C. Question 4. We have an electric kettle that's used to boil water. After the water is boiled, the temperature decreases by 22 degrees. The mass of the water is 0.5 kilograms, and the specific heat capacity of water is 4,200 joules per kilogram per degree. we want to calculate the energy transfer to the surroundings. So for this equation, we're going to use E equals mc delta T. And for this one, we're going to say the mass is equal to 0.5 because it tells us the mass of the water. We know that the delta T is equal to 22 because it's a change in temperature. And as it's talking about the energy transfer to the surroundings from the water, so the temperature in the water has decreased, so that means that that energy has gone into the surroundings. So we can keep this as a positive one. And then finally, C is equal to 4,200. So plugging in our answers, we get 0.5 times 4,200 times 22, which is equal to 46,200 joules. What are the total energy inputs to the kettle, or why is the total energy input to the kettle higher than the energy used to heat the water? So if we have the total energy, so if we have here is we have the kettle, so the kettle is connected to a plug, and that's how it will. That's a terrible drawing of a kettle, I apologise. So we've got a kettle here. Okay, terrible kettle drawing, but we can see here that the energy of the kettle, when you turn a kettle on, it's connected to the electric supply. The electric supply takes some time to heat up. So the energy has to be used to heat the kettle up. Once the kettle is heated up, then the energy can then, well, some of the energy will go to, a lot of the energy will go to heating up the water. But the first initial stage is to heat the kettle up high enough so that it will get hot enough to heat the water up. So that's where the energy is used. Okay, question 5. Different energy sources are used to generate electricity. Use the words from the below to match the correct energy source to each of the descriptions given in the table. So the first one that we have is energy from the Earth's core is used to heat water. So this one is geothermal. So that is using the Earth's natural heat, so from hot rocks, from magma, near volcanoes, geysers, etc. That's what it's using to heat up the water. Fission of uranium nuclei is used to heat water. So again, when it talks about fission or fusion, this is nuclear. Obviously, currently we use fission, but the future wants to use fusion. And then finally, gases from rotting plant material are burned to heat water. So this one is biofuels because we are using the biomaterial like plants, etc. Poo, things like that, biological things to fuel our things. So here we're using rotten plant material, the gases from that, which are burnt to heat water. Part B, we have energy can be stored in a pumped storage power station. The figure shows a pumped storage power station here. When electricity is needed, the water in the high level reservoir is allowed to flow to the low level reservoir. The flowing water generates electricity. So here we have the water at the top, and then it floats down through the turbines. As the water passes, it drives those turbines and then goes into the lower reservoir. So if we look at our words that were given here, the water in the high level reservoir stores. So this one, when you've got something that's high and then goes to low, it will have a high GPE, well, relative to this one, this will have a low or a lower GPE, gravitational potential energy. So the first one that we have is gravitational potential energy. The flowing water has, so in this case, anything that's moving or movement energy is kinetic. So we say flowing water has kinetic energy. The water turns the turbine, which connects to the generator. The generator produces something which is wasted energy. So here, electrical energy is useful, so it's not that one. Nuclear has nothing to do with this process, so let's cross that one. So that just leaves sound. And sound and heat are usually considered waste energy. Heat is not always considered waste energy, depends on what you need for. So for example, a radiator, it's not considered waste energy because your goal is to heat up. So any heat that's produced by waste is useful because it goes towards the purpose of what you want to do. But some of the time heat is waste energy, and sound is usually waste energy as well. And here is a case where sound is being described as one of the waste energies. The total power input to a pumped storage is 600 megawatts. The useful power output is 550 megawatts. Calculate the efficiency. So first of all, the formula for efficiency is E equals useful over total. And then you can either use it as a decimal, or if you want to, this is optional, times it to get a percentage. Depends what the question's asking for. Now here we obviously don't just have watts, we have megawatts. But you can be you can ignore this essentially in this type of question because the megawatts will cancel out, because you'll have 540 megawatts divided by 600 megawatts, and as in mathematically we know that if you have the same top and bottom you can cancel. So you have 540 divided by 600, which is equal to 0.9 or 90%. However, if you want to put the numbers in fully, just because you may want to do that in the exam, just to make sure, mega is times 10 to the 6 in standard form. So on the calculator you would do 540 times 10 to the 6 divided by 600 times 10 to the 6, which is equal to 0.9 as well. So again, and it tells you in the question, total power is 600, useful is 540. Calculate how much power is wasted by the pumped storage station. So when you have total is equal to useful plus wasted. So if you were to find the wasted, you would subtract the useful and move that to the other side. So it's total minus useful equals wasted. So here it's 600 minus 540 is equal to 60. And again, 60. Here's the units for you, but again, don't forget the units. That was very lazy here, so it's 600 megawatts, 540 megawatts is equal to 60 megawatts. How is the temperature of the surroundings affected by the energy wasted by the pumped storage power station? So here, if there's energy waste, usually that's thermal or can be thermal energy. So in this case, the temperature would increase because in the surroundings, so if this is the pump storage or the pump storage power station, the wasted energy is coming out the power station. So if that's heat energy, that's going to heat up the surroundings. If it heats up the surroundings, the temperature of the surroundings will increase. Okay, question 6 has some people in elevator. The motor in the lift does 1,200 joules of work. In 8 seconds, calculate the power output of the motor in the lift. So this one is nice and easy because it tells you that power is work done. So it tells you here that it does 120,000 joules of work, and we divide that by 8 seconds. So you plug this into your calculator and you should get 15,000 watts. Part B, the power input to the motor is greater than the power output. Tick 2 reasons why. So we've got energy is transferred in heat into the surroundings. Friction causes energy to be transferred in non-useful ways. The motor is connected to the mains electric supply. The motor is more than 100% efficient. There are only 4 people in the lift. So the power input to the motor is greater than the power output. So that suggests that there is lost energy. Okay, because we're going to have the total is equal to So hang on. So if it suggests that the input is greater, then usually we have input equals useful plus wasted. So that's the input energy. So you put 1,000 joules in, for example, you might get 600 joules of useful energy and 400 joules of wasted energy. So in that case, the input would be greater than the output. So here, it's just that there's some wasted energy. Energy transferred in heat and surroundings. So this is wasted energy. So that's likely to be correct. So we'll tick this one for now. Or actually, in the exam, you should tick it outside the box just in case it's wrong. Friction causes energy to be transferred in non-useful ways. This implies wasted energy, so that's correct. The motor is connected to the mains electric supply. So yes, this is correct, but it's not. This is factually correct, but it's not correct for the question. Okay, the question is looking for why is the input greater than the output. That doesn't tell us anything. That just says that it's connected to electricity, but it still may be input. It might be 100% efficient, or the electric might go to moving the lift. So this in this situation is wrong. Nothing can be more than 100% efficient, so that's incorrect. And there are only 4 people in the lift. Just no, that doesn't help us at all in this situation. The number of people in the lift doesn't mean anything in terms of the power input greater than the power output, and it's certainly less of a reason than these two. So the answer is energy transferred in heating the surroundings, and friction causes energy to be transferred in non-useful ways. Figure 2 shows part of the circuit that operates the lift motor. The lift can be operated using either the 2 switches. Explain why. So this is an electricity question, and we can say either the 2 switches. So if we close this switch and this switch remains open, then the circuit is complete. The electrons and the current will flow through this part of the switch, through the motor and back again. If we were to remove that and instead close this switch, then the electrons again will go through the power supply, and this time can't go through this way because there's no way to go through. But here the switch is closed, almost like the bridge is down, so the electrons can pass through here, back to here, and then go along to the motor and then back up to the power supply. So the reason why is that the switches are in parallel to each other. When they're in switches, so therefore closing either switch completes the circuit. So the first mark comes from here, the second mark will come from here, and that gives you your 2 marks for this question. Part D, write down the equation that links gravitational field strength, gravitational potential energy, height and mass. So this is an equation you should know. I'm going to shorten this to GPE. So GPE is equal to mass times gravity times height. You should, in the exam, don't be as lazy, write out the words if it asks you to write it out. But they most likely will accept this as well as long as you made it clear. But you should write out the words where possible. But this one is a formula that you should be comfortable with. Gravitational potential energy is mass times gravitational field strength times height. Here we have a question. So the lift goes up 14 meters. The total mass of the people in the lift is 280, and gravitational field strength is 9.8. Calculate the increase in gravitational potential energy of the people in the lift, giving your answer 2 significant figures. So GPE is mass times gravity times height. So GPE here is equal to, the mass is 280, G is 9.8, and H is 14. So plugging those numbers into the calculator, GPE is equal to 38,416 joules. However, the question wanted 2 significant figures. So 2 significant figures, 3 and 8. So we write it as GPE is equal to 3. Check that the third figure is not, check what that is. So in this case it's 4, which means that we round down. So it's just 3, 8, and then 1, 2, 3, 0. So our final answer is 38,000. Okay, question 7. Energy resources can be renewable or non-renewable. Coal is a non-renewable energy source. Name 2 other non-renewable energy sources. So non-renewable sources, we can have oil, you can have gas, and you can have nuclear, which is technically a non-renewable energy source. Even though it will last longer than any of these three, it's a finite source. So we count that as non-renewable. Finite, again, just means that it will eventually run out. There's only so much of the resource for us to use. Part B, wind turbines are used to generate electricity. The graph below shows how the power output of a wind turbine changes over the day. A wind turbine does not generate electricity constantly. For how many hours did the wind turbine generate no electricity? So we can see that it starts from 0, it fires up. We can see that it goes all the way, and then where it's 0 is here and here. This is 12, so we need to work out what the difference is between what each of these. So the 0, this is 0 to 4, so that suggests that this marker here is 2. So that means that if this is 12 plus 2, that's 14, and then it starts up again at 18. So we have 18 minus 14, which is equal to 4. So there was 4 hours of no electricity being generated before then the wind picked up again and power was distributed. Electrical power is transferred from power stations to the national grid. What is the national grid? So again, this is a little bit of electricity. The national grid is simply a system of cables and transformers. The cables carry the electricity across the current, and the transformers step it up and step it down depending on whether it's travelling long distance or whether it needs to be used in a domestic situation. So it's simply a system of cables and transformers. An island has a large number of wind turbines and a coal-fired power station. The island needs to use the electricity generated by the coal-fired power station at certain times. Choose one reason why. So the key thing here, wind is a renewable energy source. That doesn't mean anything in terms of this question, because a renewable energy source can run for 24 hours, but just in this case, wind is not one of those. But it's not a reason why we have to use coal power. Wind turbine power output is constant. As we've seen from the graph, this is not true. It depends on the wind speed, which varies, so therefore that's not true. The power output of wind turbines is very unpredictable. This is true and matches the reason. But we'll just check the last one. The fuel cost for wind turbines is very high. This is untrue. The fuels for wind turbines are free because we're just using wind. So this is a wrong statement. So therefore, correct answer is this, number 3. A wind turbine has an average power output of 0.6 megawatts. A coal-fired power station has a continuous power output of 1,500 megawatts. Calculate how many wind turbines will be needed to generate the same power output as one coal-fired power station. Okay, so we want to get a total equal to 1,500 megawatts. Now, if you're struggling to work out whether you need to multiply or divide, you can set this up as a bit of a mathematical formula. We know that our total is equal to 1, so the power of one turbine times the number of turbines. So if you've got 2, then you're obviously going to have 2 times the power, etc. So in R1, we know the total we want to get is 1,500. We know the power of 1 is 0.6, and we need to times the number, which we're going to call n. So here we can rearrange the equation. We can divide both sides by 0.6. So we get 1,500 divided by 0.6, and then on the right hand side these will cancel, so you're just left with n. Plugging that into your equation, you get 2,500 wind turbines, and that's your answer to part E. It is important that scientists develop new energy resources. The reason why, so all energy sources are running out. Well, no, that's not true because, for example, the sun is an energy resource, the wind is an energy resource, the geothermal, etc. So that's not true. All energy sources are used to generate electricity. Yes, but that doesn't really answer the question as to why we need to develop new ones. And then most energy resources have negative environmental effects. This is true. A lot of them do. Coal, oil, gas, even the likes of wind turbines, solar panels, etc. They all have some negative environmental effects. So this is very true. And this matches why we need to develop new ones to reduce the environmental effects. Question 8 is split over a couple of pages. So a student investigates the properties of 3 insulating materials. So here we have hot water that's been placed inside a metal can. Temperature gauge is placed in, and then we insulate the can. The reason why we insulate is to stop the heat escaping. So in the investigation, different insulating materials are used to insulate a metal can filled with hot water. Figure 2 shows how the temperature measured by the thermometer changes over 25 minutes. What was the temperature of the room where the students carried out the investigation? So in this one here, we can see that we want the temperature of the room is going to be the final temperature of the water, because what's happening is that if we, for example, leave it untopped with no cap on and no insulation, the water cools down and the heat energy escapes into the room. Eventually, the water and the room reach the same temperature because it cools down, and then it reaches what we call an equilibrium, i.e. there's no more change between the two. So there's no change in temperature between the outside and the water, and that means that it's at room temperature. Because heat, if there's a difference in temperature, for example, if this is hot and this is cold and they're next to each other, then the heat will flow that way. It will go from hot to cold. But if there's no temperature difference, so for example, if this is 10 degrees and this is 10 degrees, then there is no heat transfer on a basic level because they're at the same temperature. So in this situation, we want to find the one where the temperature remains constant. Here, it remains constant for material C at 20 degrees. So we can say that the room temperature must be 20 degrees. Material C has the highest thermal conductivity. Explain how it shows it. So thermal conductivity means that it transfers heat very well, and we can see that material C is very good at this because it has the biggest temperature drop. It goes from 80, very quickly reduces down all the way to 20. So therefore, figure 2 shows this because it has the greatest temperature drop. Part C, another student repeated the investigation using the equipment shown in figure 3, and he uses the following. So here he uses a bigger insulation, suggest how using the equipment in figure 3 would have affected the student's results. So the key thing here is that we've got thicker insulation, and insulation, remember, keeps the temperature, will insulate it better, so we'll stop the temperature decreasing as much. So therefore the temperature decrease will be lower. And yeah, the first mark comes from the thicker insulation, so just observing what's happening. The second part will come from the temperature decreasing, which will be lower. Part D, the students could have used a temperature probe and a data logger instead of a thermometer. So the data logger is shown on the left-hand side, which is 38.7 degrees, for example, and then the thermometer we can see measures at 38, 39. So compared to the thermometer, the data logger and the temperature probe have a resolution that is going to be higher. So resolution essentially tells you how detailed you can see. From here, a thermometer, you can only say whether something is 38 degrees or 39 degrees. Well, here you can tell if something is 38.6 or 38.7. So here this goes to 1 decimal place, and this just goes to 1 unit essentially, so 1 degree. So this one, the data logger has a higher resolution because you can see more detail, more decimal places, etc. Compared to the thermometer, the chance of misreading the data log on the temperature probe is lower. The reason why is because you have to eyeball what is happening here. So you might misread it. There's no exact value for you to do, so you're just gonna, if it's roughly halfway, then someone might go above, someone might round it down. While here, there's no ambiguity, there's no uncertainty in that. It's just going to read off the value. Also, it depends on your eye level. If you look at something like a thermometer at different angles, you might get different readings as well. And this is called a parallax error. But generally, for this question, the chance of misreading the data log and temperature is much lower than in the thermometer. Part E, the table gives information about 4 types of insulation that could be used in the walls of the house. So we've got felt wool, which has 0.07 thermal conductivity, mineral wool, then polyurethane foam, and rock wool. Which type of insulation would be the most effective in reducing the rate of cooling? So if you want to reduce the rate of cooling, then you want to use the lowest thermal conductivity because that will trap the heat more and reduce cooling. So that reduces the rate of cooling. This one is going to be the polyurethane foam. And the reason why is it has the lowest thermal conductivity. Again, it's only a couple of marks, so we don't need to go into a lot of detail for this question. Okay, question 9, which I think is the last question. Figure 1 shows a hot water tank made out of copper. We can see that cold water goes in, the immersion heater heats up the water, and then hot water comes out at the top. So copper has a high thermal conductivity than most metals. How does the rate of energy transfer through the copper compared with the rate of energy transfer through most metals? So it's got a higher thermal conductivity. That means it will have a higher rate of energy transfer because it can transfer the energy at a faster rate. So this one is higher. The tank is insulated. When the water is hot, the immersion heater switches off. Complete the sentence. Compared to a tank with no insulation, the rate of energy transfer from the water in an insulated tank. So in this case, it's going to be lower because insulation will prevent the energy transfer from the water escaping. This means that the water in the insulated tank stays hotter for longer because it stays warmer for longer. So here, if there was no insulation on the tank, then the heat energy would just flow out. Okay, it would flow out through the walls of the tank and into the room, which means that this will not stay hot, or you need a lot of energy to keep it going because otherwise the water will just cool down. If you insulate it, so if you wax stuff around it and give it like a coat almost, then that stops the heat from escaping, or at least reduces it by a significant amount, and therefore it doesn't lose the temperature as much, so we can keep it hot for longer, and therefore we don't need to use as much energy. So that's why insulation is a good thing in this situation. Figure 2 shows how the temperature varies with time, and also, so this is for a tank and immersion heater, and this is for the water for a solar panel. We have one advantage and disadvantage of heating the water using the solar panels rather than an immersion heater. So an advantage of the solar panels is that it's just continuously heated from the sun. So at least for this time frame, we will just have water. You will always have hot water on demand. So the disadvantage of using this one, first of all, it takes a long time to heat up. So because you can see here that with the immersion heater, you can just whack it up. Maybe about 45 minutes. It looks like, to get from a temperature of 0 to 58. Here it's a long stretch to get to the same temperature at 58, which is about up here. We can see it takes about 6 hours. So it's the disadvantage of solar panels is that it's longer to heat. We've got a lower temperature for most of the day. And also, you have less control of temperature. It slowly heats up. So, for example, if you want 60 degrees, you've got to wait till 5 o'clock to get that. Well, with an immersion heater, you can just turn it on and then let it go up to 60 degrees if you change the settings. So, again, you don't have as much control with a solar one then as you do with an immersion heater. During one morning, a total of 4,070,000 joules of energy transferred from the electric immersion heater. 4,030,000 joules of energy transferred to the water. Calculate the proportion of the total energy transferred to the water. So in this case, it's going to be the, again, useful over total, and that's going to be 43,000 divided by 4,000, and all that together gives you 0.99. So it's a total of 0.99, or you could also write it as 99%. Write down an equation that links power, energy transferred, power, and time. That's going to be power equals energy transferred. That's terrible. Divided by time. And that's your answer to part E. Very simple equation. Then finally, the power output of the immersion heater is 50,000 watts. Calculate the time taken for the immersion heater to transfer 4,070,000 joules of energy. Give the unit. Okay, so P equals energy over time, and we want to calculate the time taken. So we want to move time over to the left hand side. So we've got to times both sides by time. Times in time with energy over time, so that will remove this one over. So that will cancel on the right hand side, and we've just got power times time on the left hand side. So power times time is equal to energy. So here the power is 5,000. So it's 5,000. Oh no, I'm sorry, I've not read the question properly. So here we want to find time. So then we need to divide by power, because we want to move that over to the right hand side. We're doing power times time, so we do the opposite. So that ends up as time equals energy over power. Then from here we say power is equal to 50,000 and energy is equal to 70,000, so 4,070,000. So plug that into your calculator and you should get the time that is required. Oh no, I'm so sorry. Time is energy over power, so that's equal to 4,070,000 divided by 50,000. Plugging that in will give you a time of 814. So 814, and time is always given in seconds. And that brings to the end of these questions. If you have any questions or still unsure, then please do let me know.